Thank you. And while we wait for the slides to pop up, I'm Jelle de Plaa. I work at Astron here in Leiden. Actually, Astron means Space Research Organization Netherlands. So it means that we do research from space. And I'm an astronomer of origin, now also more scientific programmer. We still know quite a lot about what we're doing. So Astron is quite new here in Leiden. We moved here in 2021 from Utrecht, where we were first based, and we also have a location in Groningen. But today I will tell you a bit about the astronomy that we do. We also do some earth science. I'm in the high energy astrophysics department. And what do we do in high energy astrophysics? Basically we look at the hot stuff in the universe. So everything that is really hot, usually gases, emits light in X-rays. And I'll show you a bit more how that actually works. But you can see a lot of things actually when things are getting hot in the universe. For example, if stars explode, supernova remnants, they shine in X-rays. The stuff around black holes, when gas is swirling around a black hole, that also gets very hot. And maybe this is most surprising if you look at really big groups of galaxies and galaxy clusters, that those also attract a lot of material and gases from the Earth's surroundings and also get really hot. And these you can also see when you look at X-rays in the universe. So, just to recap what X-rays actually are and how they are formed. With our eyes we see our regular colors, right, from red to purple, a bit looking like a rainbow. That's only the stuff here in the middle. It's actually a small band of radiation that we can see with our eyes. And light is a wave phenomena, so light consists of waves with a certain length. And if you increase the length, you would go left in this diagram, and if you go a bit more longer wavelength than red, then you get into infrared, that, for example, a remote control can use. If you go further away, you get microwaves from a microwave oven that's used to heat your food. And if you go to the longest wavelength, you are in the radio wavelengths. So the radio that you listen to in your car, or these big dishes that astronomers use to look at radio emission from the sky. But those are actually a bit on the cooler end. If you go to the blue end and you make the waves shorter, then first you get ultraviolet, that you need to put your sunscreen on in the summer to protect your skin from that radiation. If you make it even shorter, you get into the X-ray regime. And X-rays, most people know that from the hospital when they see whether you have a broken arm or not. But these are actually formed when things are really hot. Here at the bottom you see a thermometer. And, well, if something is in the deep infrared, then things are really cold. You are sitting here with body temperatures of 36, 37 degrees. And you all emit infrared radiation, but we cannot see it with our eyes. But if you make things hotter, also like in the oven, when you put a grill on, if things become hot, they become red glowing. If you would make them even hotter, it becomes yellow, white, hot. So what we see is kind of around 5,000, 6,000 degrees. And that's the surface of the sun, more or less. But if you make it hotter and hotter, into millions of degrees, then things start to emit X-rays. So everything we see from now on in this presentation is millions of degrees hot. So, just to show what the sun looks like, this is actually a rainbow, as you would see them at the sky when we have a shower in the days. And if you really stretch that rainbow into the really small things, you start to see little black bars in there. And that's because there's gases in the sun that absorbed a little bit of this light. It's very specific colors. And it looks a bit like a barcode. And so this is the barcode that you see in the supermarket. and where you can recognize what kind of product it is. It's kind of a code. But astronomers can learn a lot from these absorption features, or sometimes they are even giving light. What happens in that object? So, for example, if you just have a hot gas somewhere in the universe, what you usually see is that in this rainbow you see some colors enhanced. So there's more light in certain colors. And if you have some light source and something in between, and in our sun, actually the light source is deep within the sun, that's producing light, and the outer parts of the sun are absorbing a bit, then you see these black stripes in your spectrum. And this is what we see in visible light, but we can also see those in infrared and in X-rays. So, what is the current state of the art of seeing this in the universe? Actually, X-rays we cannot see from the ground on Earth, because we have the atmosphere above us, and that's actually pretty good because it protects us from all the radiation that is out there in the universe. So if we want to see X-rays from the sky, we need to be in space. And that's why I'm in the Space Research Institute. We launch satellites or instruments on satellites to look at that. Now this is the CRISM satellite, maybe not the most well-known one, but this is a Japanese satellite that was launched in 2023, and I will show a quick video of that when it was launched. But this is an X-ray telescope, and it has some mirrors at the front here, and in the body here there are a couple of very sensitive detectors to measure very carefully the color kind of X-rays. Of course, well, we cannot see these colors, but it's kind of the wavelength of these X-rays. And well, these mirrors are a bit special, but these are not the most special mirrors, but that's for the next speaker to talk about how you actually put X-rays through a mirror and see something. But let's first see how this thing got launched. Let's see if it wants to run. Yes. So this is actually the 4th time that we tried to launch a mission like this from Japan. It's a Japanese mission, and somehow the previous attempts always something went wrong, and actually this time also a little bit, but luckily not catastrophic. This was at least a successful launch attempt. We were very happy with that. And this puts the satellite in a low Earth orbit, around 500 kilometers above the surface. It goes around the Earth in about 1.5 hours, and from there it can look at the X-ray sky. It's always very spectacular. But in this satellite there's a very special detector. If you have a camera here, you have some on your phone, you have some pixels there. Well, that's a really tiny square on your chip that is sensitive to light. And in your phone there's so many megapixels. Well, in this detector, I have to disappoint you, there are not that many pixels. This is an image of this. And here you see, if you look carefully, 6 times 6 squares, so 36 pixels. So this is not really imaging yet, but these are really special pixels, because they have some superconducting material in there, and this is a kind of a blow-up of such a pixel. The idea is that you put this to really low temperatures, almost at 0 Kelvin, so at the lowest temperature possible, only 0.1 degrees above that. And superconductive materials at that temperature have a very special property that below a certain temperature there is no resistance at all in that material, so then the current can go freely. But then there's a very steep transition from this superconductive to normal conducting. And that's this graph. So if you are at really low temperature, the resistance is really low, 0. And at some point, there's a very steep transition where the resistance becomes normal here at the top right. And you can use that. If you make the temperature such that the system is kind of here below, and then you let an X-ray fall on that pixel, then the pixel becomes a slightly bit warmer. So then the temperature goes a little bit up, but then the resistance reacts a lot faster. So it's kind of an amplifier. And in that way, we can really measure the energy of this X-ray very well. Because every X-ray dumps its energy in this pixel, it heats it up, and with the electronics we can measure how energetic it was. And if you put this thing in space and point it at nice objects, you can make graphs and see what actually happens there. So I promised black holes, so here is one. This one is an artist impression because most of these black holes are way too far away to really see in this manner. We would like to see it like this, but well, maybe you don't want to get this close either. So here in the center, this little black dot is the black hole. And these kind of beasts, because this is a pretty large one, you find in the center of galaxies, in the kind of the biggest group of stars. And around this black hole, of course, gravity is quite strong. If material is falling in, it's actually not falling in directly, but it starts swirling around it and becoming hot in the process. So very close to the black hole, the velocities are very high, and a bit outside, the velocities become a bit slower, and at the outer edges, it's probably the slowest. And you can imagine that, well, this picture is maybe not complete. If you have this hot material here, there's a lot of things happening. Things blow away from there because it's hot, just like the solar surface. There's also a lot of things happening. But yeah, we cannot see this directly, so how do we know this? Well, that's where our barcode comes in. So if you have this barcode, but then put it into a graph, like how much light you see at a certain energy. So here in the horizontal axis, we see I want to be here. Here we see the energy of the horizontal axis, and basically the vertical axis is how much light we have. And that's the X-ray brightness. And in this is a real measurement from this satellite. And you can see that there is a very sharp peak, and there's also peaks, or actually dips, here on this side. And we know that this is a peak caused by iron, so the metal, which is in gas form there. And there's also these dips. So we've learned that when a gas is there and emitting, you usually see these emission lines, so you see a light emission, and if something is in front, then you can see absorption. So both is happening here, and these are also shifted somehow. Well, if you hear a car go by, when it's approaching, it's like, well, the same happens with light. If something is coming toward you, the wavelength becomes a bit shorter. If things are moving away from you, they get a bit longer. So here we see these dips here. They can be from the same line, but then shifted because of velocities. And we find that in this black hole, there are gases actually being ejected, sometimes up to a third of the light speed. So 100,000 kilometers per second. So that's really, really fast. So there's a lot of things happening there. But also, for these peaks, you can make, you can also kind of derive whether our model of how a black hole looks, whether that's correct. So when you dissect this peak, And if you really look at it with high resolution, it is a bit small here perhaps for in the room, but it, oh, here you see that if you have this cross-section of this whole system, here's the black hole, and here's this gas that is swirling in towards it, then in the middle here, this blue part, there the velocities are the fastest, and then the further out you go, the velocities become slower. And since this is all going around, one part is coming towards us, another part is going away from us, some parts are kind of stationary, it becomes a bit like a bump. And the sharpest part of the bump is where the velocities are the lowest, so the center part of the line is the emission from the outer part here. Then there's a little bit broader part, and that's probably more inward. And if you really look carefully, there's also something that is really broad, and that's emission from the center part. So in this way, you need to maybe a bit of imagination, but you can figure out whether what we think this structure is, whether that is consistent with our observations. So that gives an astronomer a picture in their mind what this must be look like around the black hole. So we are just starting to measure all kinds of black holes in the universe. This is a slightly different one, but we see this pattern quite often. So this is, here you see a galaxy and a very bright star kind of in the center, but this is not a star, this is actually the black hole. And from that you can see this spectrum with a Japanese satellite with a big iron line here and all these smaller lines here, which is all gases being blown away from the system, even up to very high speeds. So this is what I wanted to talk to you about. One of the results of this new mission. Thank you very much. Are there questions? Questions you have?
Why is the iron line specifically so pronounced?
Well, iron is a pretty abundant element in the universe. It is kind of an end product of supernova, a particular kind of supernova. So there's quite a lot of it. And also at this temperature, the iron that we're looking at here, if you have some chemistry, you may know that iron has 26 electrons normally. But in these gases it's so hot that there are only 1 or 2 electrons left. And this is kind of like a hydrogen atom with 1 electron circling the core. But in this case, the core is 26 protons with neutrons, a very heavy one with just 1 electron. And that's a very strong source of lines. And a line is formed by transition of some electron that goes into a different orbit. And that is causing these strong lines. And then?
Thanks for your talk. So you showed this picture of the pixel resistance as a function of temperature.
Yes.
And so it's a very narrow range of temperature change that you have to target, I guess. The moment you jump a little bit, a little further, then you cannot really see anything anymore. Is that correct?
Yes. Yeah. So we are building also these things at Esron in Leiden, and it's indeed a design challenge to choose the material such that that this range is exactly in the range of X-rays that you're interested in. So we can build them such that they're sensitive between, let's say, 1 and 10 keV. That is the energy range that we are interested in X-rays. So you can also make them for a different range, but then you need to change the materials and kind of shift this transition to a slightly different temperature. or make it flatter. But it all has to do with how thick do you make it, what kind of materials do you use, and then you can tweak how sensitive it is in a certain range.
So your detector is really sensitive to a range, and that's it. You cannot really make it flexible in an easy way.
No, you cannot make it in a broadband really easily. So at some point you cross over here, and then your resolution goes down, and then it's over. Oh.
Yeah, okay, so you said the telescope is operating already a year or two, right?
Yeah, it was launched in September 2023,
Yeah.
so it's now 2.5 years in orbit. So
yeah, and what would be like one of the breakthroughs that so far came out of the data? What would you say?
yes, so it's also one of the things that is related to the black holes, because what we are looking for, maybe I can go forward again. Yeah. It's coming. Let's see. I think I need this one. This very broad line here, because what we are also hoping to find is if you get close to the black hole, you get also all the effects of general relativity. Space-time gets folded in all kinds of weird ways, and you should also be able to see at some point a very particular shape in the line of these effects. And with the previous instruments, we thought that we saw that, but in reality, when we look at these data, sometimes we see that it's not that pronounced, but there's other lines there that kind of mimic that behavior. So that way we were learning much more about what we actually see and how close to the black hole we can get.
One question about the microcalorimeter that you talked about for the detector.
Yeah.
What sort of materials?
That's a good question. I'm not the expert on that, but no, I need to look that up. What material combination that especially is.
I'm just curious because when you were talking about the launching of the satellite, you said some things went wrong, and I just got curious what type of things, or if it was something that could impact the data.
Yes. Well, the first attempt was already 25 years ago, and there the rocket didn't work properly, and the satellite didn't reach orbit and fell down. The second one, there was a mistake in the design of the cooler, because you need to put this in a kind of big refrigerator, and the refrigerator was actually leaking somehow, so it lost its capability to cool really quickly.
But there were no major issues with the successful launch, right?
No, then the launch was successful. The third time, the launch was also successful, but then there was a mistake in the attitude, so the satellite needs to be pointing, and there's a system on the satellite to make sure that you go to the right direction. But there was a mistake in an update of this software that does that. And at some point, the satellite thought, like, oh, I'm turning, and it wanted to compensate to get straight again. But there was a minus sign somewhere wrong, and then it started going too fast, and it kind of spin out of control, and then broke up, unfortunately. That was 6 weeks after launch. So, well, I was on the science team, so you can imagine that it was a bit of a bummer that your observations were not going to be taken. And that was in 2016. And now we have this mission, which went fine for 95%. But before you have this cooler, and you have this very sensitive detector in it, so you want to protect it during launch. So on top of this cooler, there's a small door that protects it, but after the launch, when everything is okay, you want to open the door and then look at the sky. But here the door didn't open. Luckily the door is not very thick, so it's a very thin door, so we can see X-rays coming through it. But we would like to see from kind of 0.2 keV to 10 keV, but now we can only see from 2 keV to 10 keV, so all the low energy part is gone.
Yeah, I was wondering if you have to do some sort of data correction to account for the fact that the door is closed.
Yes, so luckily we have the information what the door is and what it's made of and what the properties are, so we can correct for it. But yeah, we get less photons now than we would like to have. Last week, in summer last year, we had an attempt to shake the satellite a little bit to see if the door would open anyway, but unfortunately, no.
I have a question about this in particular. When you guys are measuring the X-rays, is this one spectral band that was like decomposed, or is that 3 different measurements?
This is actually one measurement decomposed. So what we see is the green-bluish thing in the back. That's this histogram, and on top of that are models. So what we calculated would be, and we try to kind of, if you add these lines up, then you would get the total shape of the spectrum. So we try to decompose it into several parts, so see if we can model this bit and that bit separately, and if you add it up, whether it's mimicking the whole thing. Yeah, on the top.
Hopefully in 11 years, new Athena will be launched, and it features a larger mirror and also an array of microcalorimeters with smaller pixels, much larger array. What do you think it's going to change? Can you tell us why it is necessary, or is it necessary?
Yes, so what will really change is, as already said, like this calorimeter has 36 pixels, which is really not much. Also the mirrors of this mission are not as expensive or not as good as we can make them now. So for black holes, it doesn't really matter whether you can make an image or not, because you will not see anything, and you will just see a star. But if you look at supernova remnants, exploded stars, or these clusters of galaxies, then you would need both imaging, and so you want to make an image, and you want to analyze the spectra at the same time. And that is where Athena will shine, because then we will have 1500 pixels instead of 36, and a much better mirror that the next speaker will talk about. And that will really change our view of the X-ray universe.
Thank you.
No questions? Okay, great. Then